everyone, today I'll be talking about the Ka and the pKa values of acids and the speciation of an acid at a specific pH. So this is a general dissociation reaction of a monoprotic acid. The strength of an acid in solution is represented by the acid dissociation constant Ka, and this equation here corresponds with a monoprotic acid with the dissociated product in the numerator and the undissociated acid concentration in the denominator. So the pKa is the negative logarithm of the dissociation constant Ka, and it is used to determine the speciation of an acid at a certain pH. So we can determine at what pH will the acid release its proton. So pKa values are constant, and the table to the right here has the pKa values of some important acids. So an acid with one pKa value are monoprotic and can donate one proton. Acids with two pKa values are diprotic and can donate two protons, and acids with three pKa values are triprotic and can donate three protons. So the acid species is determined by the pKa of the acid and the pH of the solution that it's in. So for a monoprotic acid, it has one equilibrium point where the acid equals its conjugate base in terms of concentration. That is when pH equals the pKa value. And when the pH is less than the pKa, it's in its most protonated form, and when the pH is greater than the pKa, it's in its least protonated form. For diprotic acid, it has two equilibrium points where the most protonated form can equal the second least protonated form when it releases its proton, and that is when the pH equals the pKa1. And when the pH is less than pKa1, and it is in its most protonated form. Second equilibrium point is when the second least protonated form equals its least protonated form, and that is when pH equals pKa2. And when the pH is greater than pKa1 but less than pKa2, that is when it's in its second least protonated form. And when the pH is greater than pKa2, it is in its least protonated form. So an example here is carbonic acid, which is a diprotic acid with pKa values of 6.3 and 10.3. And the plot to the right is a dissociation plot where the carbonic acid is looked at over a pH of 2 to 14. So when the pH is less than pKa1 here, which is 6.3, the most abundant form is H2CO3 here. And when the pH equals pKa1, that is this point here where the red line and the green line intersect, and that is when H2CO3 concentration equals the HCO3 minus. And when the pH is less than pKa2 but greater than pKa1, it's this region of the plot here where HCO3 minus is the most abundant. And when the pH equals pKa2, it is this point here where the blue plot or the blue line intersects with the green line, and that is when HCO3 minus equals CO3 2 minus. And when the pH is greater than pKa2, it's this region of the plot here where CO3 2 minus is the most abundant. So let's do an example problem where we determine the speciation of hypochlorous acid at pH 5. So we must consider the pH of hypochlorous acid, which is here, it's a monoprotic acid, so we'll have one pKa value of 7.53. So the pKa is greater than the pH, And going back to the previous 2 slides, we can see that when the pH is less than the pKa, it's in its most protonated form. But when the pH is greater than pKa, it loses a proton, so it'll just be HOCl-. So the speciation of sulfurous acid at pH 5, we must consider the 2 pKa values because it is a diprotic acid, so it has the ability to lose 2 protons. And let's just write out the 2 pKa values here, which is 1.85 and 7.19. So pH 5 is in between these 2 pKa values, so let's just write that here. So going back to the previous 2 slides where we are talking about the pKa values of diprotic acids, we're looking at this region here where pH is in between the 2 pKa values. So when the pH is equal or less than pKa 1, it will be in its most protonated form, and when it is greater than pKa 2, it's in its least protonated form. So at pH 5, it's right in the middle where the sulfurous acid has lost 1 proton because it is greater than pKa 1. So in summary, when the higher the Ka, the stronger the acid, because high dissociated product concentrations means that it's a strong acid, and the lower the pKa, the stronger the acid, because it means it has a high affinity to dissociate at a lower pH. And just based on the equation, the negative logarithm of Ka means that the lower the pKa, the higher the stronger the acid. So looking at these examples here, we're calculating the Ka values of the following acids and remembering the equation that the pKa equals the negative log of Ka, which means that the Ka is equal to 10 to the power of the negative pKa. So for hydrofluoric acid, we'll look at the pKa value, which is here with 3.18. So the Ka value would be 10 to the negative 3.18. Which is 6.6 times 10 to the power of negative 4. So for chromic acid, it has 2 pKa values because it has it's a diprotic acid. And has these 2 pKa values of 0.2 and 6.51. So the first Ka value would be 10 to the negative 0.2, which is 0.63, and the second Ka value would be 10 to the negative 6.51, and it'll have a value of 3.9 times 10 to the negative 7. So in the next example, we're going to determine if the following acid is strong or weak and calculate their pKa value. So this arbitrary acid has Ka values of 0.003 and 2.5 times 10 to the negative 7. So remembering the pKa equation is the negative log of Ka. We don't need to rearrange the equation or anything like that because the Ka values are given and we're looking for the pKa. So the pKa1 will be negative log 0.003, which is 2.5. And the pKa2 is the negative log of 2.5 times 10 to the power of negative 7, which equals 6.6 times, or just 6.6, sorry. And looking at the first pKa value, which is representative of the most protonated form dissociating to the second most dissociated form, it has a low value of 2.5, so that means it is a strong acid. So just going over, the base has a Kb and refers to the Kb and POH, where this equation at the top here is a base reacting in water, where the strength of a base is based on its ability to accept a proton and release hydroxide ions when in solution. So the Kb is a dissociation constant. So in summary, an acid dissociation constant Ka measures the strength of an acid in solution based on the concentration of dissociated product over an undissociated acid. pKa indicates the speciation of an acid based on the pH, and it is determined by the negative log of Ka, where a high Ka and a low pKa corresponds to strong acids, and a low Ka and a high pKa corresponds with weak acids. Base dissociation constant Kb measures the strength of base in solution based on the concentration of the conjugate acid product or the protonated base and the hydroxide ion concentration over the base. High Kb corresponds to a strong base and a low Kb corresponds to a weak base. Additional practice problems, including the examples done in this video and the answer key, are linked in the description box below. And the next video will be talking about the pH and the POH along with examples.